Greetings everyone, this is Non-Expert here back again with another video. Today we are going to be solving problem number 43 and the difficulty it's been rated at is easy. This problem was asked by Amazon and let's just get down to the problem description. So we need to implement a stack that has the following methods. The first method is a push function which sort of pushes an element onto the stack. A pop function is just going to pop off and return the topmost element of the stack, and if there are no elements in the stack then it would throw an error or it would return null. And at the end we have a max function which returns the maximum value in the stack currently. If there are no elements in the stack then it should throw an error or return null. The entire basis or the entire approach to go about this problem, even whenever you ask this in an interview, is the fact that you want to understand what all memory restrictions that you're working with and what's the time complexity that you're working with. Over here we've been given that there are no memory restrictions whatsoever. Each method needs to run in constant time. So basically the complexity of each of these functions, the push, the pop, and max, is going to be working on O of 1. And this is just a variant of a pretty famous problem, and the name of the problem is the min stack problem. Unfortunately, we were able to find it on LeetCode. Again, I would urge you to pause this video and check out the link given in the description below and try solving this question on your own. This is pretty simple. It's been rated as easy in LeetCode as well. And the only difference over here is that you have two functions, and the first function is the top function, which returns the topmost element, and you have a get min function instead of a get max function, where you retrieve the minimum element in the stack. So just to give you some more clarification on this, we would be working with O of 1 complexity. So our time complexity or like our time performance should be really good, but our space complexity is something that we don't really need to worry about. Um, and the way we would sort of want to go about it is we would want to maintain two stacks. One would be the normal stack and the other would be a min stack. So let's just make a simple representation. Let's just say that we have these elements, which is 2, 3, 4, 1, 5, and all these things are going to get pushed inside one by one. So what's going to happen is we are going to have we are going to be using Python lists over here, and the way Python lists works is that you can sort of use them as stacks itself, because the way the properties are designed inside the Python list, or the functions, the way they've been built out, whenever you do an append, it sort of appends at the very end of your list, and whenever you do a dot pop without giving any parameters, it pops out the last value. So you could sort of use that in order for you to implement a stack. And again, the two functions that we would be using would be the append and the pop. So that's something that we really need to remember. And let's just sort of have a look at it. So you have append and you have pop inside your list. And basically we're going to have two functions. So let me just represent this. You're going to have a stack and you're going to have a min stack. Let's just, beautify this a little. Now what's going to happen is, the stack is obviously going to keep on pushing the elements as they're going to be coming inside, and the topmost element is going to be the topmost element inside the stack, or the last element inside the list is going to be the topmost element inside a stack. So whenever we do it two, the min stack is also going to work in conjunction with the pushing of those elements. So whenever you have two, it's going to push in two, and then whenever it's going to have whenever another element is going to be pushed inside your stack, what we're going to do is we're going to try to analyze or try to understand whether that element, the number which is getting pushed, let's say 3, if it's sort of greater than, or whether that rather if it's less than 2, then we sort of push that inside the min stack instead of the, basically we're just pushing the minimum value between them. So the representation would be that you have 3 here, but 2 is going to be appended here because that's the minimum. Then when 4 comes, 4 is going to be compared with 2, which is obviously um, less, and then we're going to keep on going on from there. So basically whatever element is coming inside, we're just comparing it with the topmost element inside, or the last element inside our min stack. So when we encounter 1, what's going to happen is it's sort of less than 2, so 1 is going to get pushed inside your min stack, and that's basically it. Again, there's not much here to it. Let's just get down with the implementation. So again, we're just going to have two things. The first thing is going to be a stack, and the other thing is going to be a min stack. So let's just do that, and that's just basically our entire init function. We have a stack and a min stack, And the way you want to go about, the approach of pushing elements inside your min stack is by basically you're going to check that, hey, if there's nothing inside self.min stack, whoops, if there's nothing inside, then you just do a simple append. So we'll do append of the element which is being given to us in our push function as parameter. And if it does exist, then we need to compare what's the minimum element so far. So the way you want to go about it is just say, hey, self min stack needs to do an append between whatever's the minimum element between the topmost element inside the min stack and the value x which has been passed on to us. So the way to do that, or the way to check the last element, is just do -1 in Python. That sort of returns the last value, uh, and you do that min with the x as well. So basically whatever's the minimum between these two guys, that's going to get appended to our min stack. And obviously the self.stack is just going to work as a normal stack. We're just going to append it normally. And that's basically it. So that's our entire push operation. All you're doing is you're just appending those values inside your self.stack as you normally do inside your list representation. And the only difference is that you're making sure that min.stack has the correct minimum value which is there inside the stack so far. So whenever you do a pop, all you have to do is you need to pop out min stack. So you'll just say pop, and this is just going to pop out the last element inside of min stack, or the way you can sort of think about it is the topmost element inside of min stack, and the same exact thing for your stack element. So you're just going to pop over here, and that's just going to pop out the elements. Now the top method just requires you to return the topmost element inside of self.stack. So the way you can do that, you can just say, hey, self.stack last element, which is the topmost element, needs to get returned. And for the get min function, you need to do the same exact thing, but for the min stack. So you just do that, and you return the topmost element inside the min stack so far. And that's basically it. There's not much here to it. Let's just try running this code, and hopefully this should run fine. As you can see, everything is running fine. The expected output is the same as the output which we have taken out. And let's just submit the solution. And awesome, you can see that's running 91% faster than all Python submissions. Again, we didn't really care about the memory usage. That's why it's so less. And that's basically our entire approach. We want to do it in O of 1 complexity, which we have achieved. Uh, and that's basically it. Again, if you had any doubts or if you have any comments, you can give it in the comment section below, and I'd love to solve any of your doubts. And if you did like this video, do give a like and do subscribe to this channel. We are discussion over here, and we would love to have you on board with us. And if you've already subscribed, you're awesome. We all know it, and have an awesome day. Thank you.